Okay, good morning, everyone. It's my pleasure to make a presentation here. My name is Jiahao. I come from Tsinghua University, and currently I'm also a visiting student at George Mason University. This work was done with Qi Li, Ren Jiexie, Kun Sun, Guofei Gu, Mingwei Xu, and Yuan Yang. We introduced a new attack on SDN, which disrupts control channels via shared links. Okay, this is outline. First, we'll introduce some necessary background on SDN. Then we'll introduce our attack, the related challenge, and the method named Adversarial path reconnaissance to solve the challenge. Next, we show the evaluation of the attack in a real SDN test bed. Finally, we discuss possible defense and conclude our work. Okay, let me first introduce software-defined networking. Well, software-defined networking is a new network paradigm. It separates control and data planes with a centralized controller. So SDN greatly promotes network programmability. The right figure shows the three-layer SDN architecture. The top is the application layer, where SDN applications enable various network functionalities. The middle is the control layer, where a centralized controller manages applications and interacts with switches. And the bottom is the data plane layer, where SDN switches enforce network policies according to control channels. Well, in SDN, control channels is the key part. It delivers all control traffic from the controller to the data plane. So failure control channels can result in various disasters and may affect entire SDN. So security and reliability of the control channels are of great importance. Well, in this paper, we uncover a new attack named CrossPath to disrupt SDN control channels. This attack is caused by shared links between paths of control traffic and the data traffic. Well, this attack allows data traffic to disrupt control traffic. And as the attack disrupts SDN control channels, so it can affect a wide range of SDN functionalities. To launch the attack, we assume that the attacker has compromised a host inside the target SDN. And the target SDN applies in-band control. Here, in-band control means that SDN switches forward data and control traffic at the same time, which is a convenient way to build SDN networks. Okay, let's first see a toy example. The main idea of the attack is that a malicious host sends data traffic to congest shared links that delivers both data and control traffic. Now let's see this figure. There are 5 switches, 2 hosts, and 1 SDN controller. The dotted blue line is the control path. Switches and controllers communicate with each other in this control path. And the purple line is the data path between 2 hosts. Host H1 can send traffic to host H2 over the data path. So as you can see, the link between S2 and S3 is a shared link. So if an attacker floods the data path, then control traffic passing the shared link will also be congested. Consequently, 2 switches, S1 and S2, will be affected by the attack since control traffic from the 2 switch to the controller will be significantly delayed or dropped due to congestion. So the challenge to launch the attack is to how to find a data path that contains shared links. So one way is, can we randomly choose a data path to attack? Well, this will result in low success ratio due to there are only a few shared links in SDN switches. For example, assume there are only M switches in total. The total number of links in the networks will be OM squared. However, there may be only OM shared links connecting the switches with the controller. So can we apply existing scanning tools to find such a data path? Well, this is not ineffective due to unique SDN data plane forwarding behavior. In SDN, there are no IP addresses in switch ports, and there may be no TTL decrease for packets passing SDN switches. So scanning tools like traceroute that depend on IP addresses in switch ports and the TTL decrease will not work in SDN. So how to solve the challenge? Well, we present adversarial path reconnaissance. The key observation is that control path delays can be an indicator on whether a data path contains shared links. Still, this figure. When the attacker congests the data path contains shared links. So the control path delay between the switch S2 and the controller will be significantly large due to control traffic congestion. So if a data path contains shared links, an attacker can congest it, then the attacker can get the large control path delays. So let's see another case. If the data path contains no shared link, what if the control path delays? Well, the control path delay will be small since control traffic will not be affected by the data traffic. This figure shows the control path delay in such two cases. We can see that the control path delays in the two cases are significantly different. So we can leverage the control path delay to find whether a data path contains shared links. And how to measure control path delays with an end host? Well, we find that we can leverage side effects of dynamic flow rule installation in SDN to measure them. Let's see this figure. Suppose H1 sends a new flow to H2. When the first packet of the flow arrives the switch S1, since the switch has no flow rules, the first packet will be sent to the controller. After rule installation, the packet will be sent back to switches and be forwarded. So H1, the round trip time of the first packet contains the data plane forwarding delay and the control path delay. However, the round trip time of the second packet will only contain data path delay because existing rules has installed in the two switches. So an attacker can measure the control path delays based on the first two packets of new flow. So let's summarize the algorithm of our reconnaissance. First, an attacker chooses a data path. Then they flood data traffic to the data path. And at the same time, he measures the control path delays. If the delay is large, then the attacker finds a target data path that contains the shared link. If it is small, then the attacker should try another data path. So in our paper, we also provide some techniques to improve the accuracy and efficiency of our reconnaissance. For example, to reduce the impacts of network jitters and to enable concurrent reconnaissance. Due to time limit, please see our paper for details. So to evaluate the effectiveness of the attack, we conduct experiments in a real SDN testbed. The testbed contains commercial hardware SDN switches and an open source controller floodlight and the physical host connecting to switches. And we replay 5 types of real traffic trees as the background traffic. And we evaluate the accuracy of our adversarial path reconnaissance and the degradation ratio of control traffic. As you can see in this figure, although different types of background traffic affect the accuracy and the control traffic degradation, however, we can see that the accuracy always achieves more than 80%, and the degradation ratio always achieves more than 85%. Moreover, as almost all SDN applications depend on control message delivered in control channels to enable network functionalities, so the attack can affect a wide range of SDN functionalities. Well, we measure the impacts on 3 popular SDN applications, including ARP Proxy, Reactive Routing, and Load Balancer. Now, we first see how the attack affects ARP Proxy. Well, ARP Proxy is a basic service in SDN. Our attack can significantly decrease the ARP Proxy, the performance of the ARP Proxy. The left figure shows that the ARP throughput significantly decreases when the ARP request rate achieves 300 packets per second. It drops from 3,000 to 20. And the right figure shows that most ARP query delays remarkably increases with the attack. Now let's see the attack impacts on reactive routing. The left figure shows that the success ratio of raw installation. We can see that without the attack, the success ratio always maintains more than 90%, regardless of the arrival rate of the new flows. However, with our attack, when the arrival rate of new flows is high, then the success ratio significantly decreases. And the right figure shows the host migration time. Without our attack, the host migration time can finish within 5 seconds. However, with our attack, the host migration will finish within 15 seconds. And this figure shows another anomaly of reactive routing due to our attack. We can see that our attack first deactivates a link, then the topology is recomputed, so a routing path is also evicted. Finally, let's see the attack impacts on load balancer. As shown in the left figure, load balancer will balance the traffic among 2 servers without the attack. However, with the attack, the port utilization of server 2 is overloaded. We find that load balancer incorrectly balances traffic among servers under the attack. So to defeat the attack, we provide 2 possible defense. The first is to deliver control traffic with a high priority. This can be implemented with priority queue or weighted round-robin queue. And the second maybe to proactive reserve bandwidth for control traffic. This can be implemented with SDN major tables. So let me conclude our work. First, we show that data traffic passing shared links can congest control traffic to disrupt SDN control channels. Second, a data path containing shared links can be formed by measuring control path delays and leveraging the side effects of dynamic rule installation. Third, we hope our work can draw more attention for network administrators. They should enable priority queue or proactively reserve bandwidth for SDN control traffic to protect control channels. That's all. Thank you.
All right. This is Qiao from Rice University. So the first question is, how do you overwhelm one link? Is it like link flooding attacks?
How do I congest one link?
Yes.
There are two methods. First is you can simply flood this link, send this traffic, and since the control traffic use TCP protocol, you can use some attacking techniques such as low-rate TCP DOS to congest this traffic, and this will low-rate TCP DOS will reduce the attack traffic, the volume of the attack traffic.
Yeah, I think using a low-volume TCP attack like this or pausing attack makes sense because we only have one host compromised, right? How many hosts do you have to compromise to launch this attack?
In this attack, we assume one host is compromised. If one host is compromised, the most efficient way to congest the link is use low-rate TCP. Because if you directly flooding the link may not be congested in some case if your link is have enough bandwidth.
Yeah. So is the sender compromised or the receiver compromised? Or, OK, that's no difference. But only one host of the TCP connection is compromised, right?
Yeah.
So you send pausing attacks from the compromised host, but you have to have another normal client to cooperate with the sender. So in the other side, which is a normal host, which is not compromised, we can easily detect the distribution of the volume, right? So I believe that we can easily detect this attack by running a simple script in the other side of the TCP host. So also you have to send a probing message more than one times to probe the target link, right? So if we can detect this attack when you first time probe the links, why this is, how can you launch persistent attacks in the network?
Because first, if you want to probe the link, then the duration of the probing is small. So it may not be easily detected because at your probing, you can first probe a link at a small duration, and after that you can wait enough time. For example, you can wait several seconds after you conduct the next probing. Then, so the average probing traffic will be small.
Okay, so basically the duration is small. So another question is...
So in the interest of time and fairness, we have another question that's been waiting for a while. This sounds like a great conversation to continue offline.
Right, thanks.
Yeah, thank you for the presentation. So actually you have assumed that the...
sorry, could you speak louder?
Okay, see. So you assume that all kind of the control traffic and data traffic are equally handled in the case of the SDN in-band, right?
Sorry, could you speak it again?
Yeah, so I mean that so you are assuming that all kind of the control traffic and the data traffic are equally handled in the case of the SDN in-band, right?
You mean the assumption of in-band control?
Yes, your assumption.
Okay, that's a good question. Actually, when we submit our papers, the reviewers also ask questions about this. So whether the in-band control assumption is realistic. Well, we first actually say that...
my question is that usually you finally mentioned that the possible defense is using the priority queue for handling the control traffic, right? But that is the common way to handle the control packet in the case of the SDN in-band. So I mean that why did you assume like the, I mean, I'm wondering that your assumption is right or not actually.
Sorry, could you speak, repeat the
I think he's
question
asking, I'm not sure I fully understand the question myself. I think he's asking about maybe something to do with the queuing that's in the network. And since there's clearly some communication issues, this might be another question to maybe discuss after the session offline.
Yeah.
Thanks. Very quickly, while our next speaker goes ahead and sets up, we have time for one more question.
Hi, I'm Ben Desfuli, Santa Clara University. So my question is, why don't you slice the network, the bandwidth, for control traffic and regular traffic, and just simply use open flow counters, you know, by the controller to, because if you slice it, for example, let's say 5%, 10% of the bandwidth is allocated, you know, for control traffic, you can always collect these open flow counters, for example, and then just look at those counters and analyze the traffic to see if there is any malicious traffic or the network is being flooded. Wouldn't that be a simpler solution? Instead of introducing an active flow in the network to flood the network, because that would also contribute to the network congestion?
Yeah, use the counters to detect traffic, maybe a possible solution to defend the attack.
Okay, thank you.
Okay.
Wonderful. All right, let's thank our speaker.